Welcome. In this video we'll present part 1 of the science of the generic carbon budget model, GCBM, which is based on the same science as the carbon budget model of the Canadian forest sector, CBM-CFS3, that has been used by the global forestry community for over a decade. Topics covered in this presentation will include representation of stand-level dynamics, including biomass, dead organic matter, or DOM, and disturbances. In part 2, we'll discuss landscape level dynamics, output indicators, and how carbon pools in a project are initialized through a background process called spin-up, identical to MakeList in the CBM-CFS3. The GCBM represents above ground and below ground biomass pools, including foliage, other, merchantable stemwood, coarse roots, and fine roots, and it does this for the softwood or coniferous and/or hardwood or deciduous component of each stand, so you can have up to 10 live biomass pools represented for each stand at any time. First, we'll describe the dynamics of the biomass pools and then discuss how they are linked to the dead organic matter dynamics and pools. The GCBM grows stands over time based on yield curves supplied by the user. The concept of yield curves is applied to strata, meaning that the model stratifies the ecosystems based on the spatial unit, perhaps the forest type, perhaps the site index or productivity class, and the user employs whatever classifiers they wish to define how their different stands grow. They can employ empirical yield curves or yield curves developed for projections, for example to be used under climate change scenarios, to represent the biomass dynamics in the ecosystem for both the softwood and hardwood components, if both are present, of each stand. Each of these has 4 above ground biomass pools. The model actually combines the submerchable and the other. The other pool includes tops, branches, stumps, and non-merchantable trees and saplings, and then there is the merchantable stemwood pool, which includes merchantable stemwood and stem bark, and the foliage pool. And there are also 2 below ground biomass pools, coarse roots and fine roots, defined as less than 5 millimeters. The user must provide the model with yield curves that define merchantable volume over age, and the merchantability criteria are set according to the province or territory selected for a project, so that they are consistent with the merchantability limits used to develop the associated volume to biomass coefficients for species or forest types in that jurisdiction. As such, it's ideal to use yield curves developed with the same merchantability criteria as the jurisdiction assigned to projects, and you can view the limits for Canadian jurisdictions in Appendix 2 in the CBM-CFS3 User's Guide. Note that merchantable volume typically does not appear in a stand until after 10 to 30 years of growth, depending on the species and location. As such, assumptions need to be made about what happens between stand establishment and the first merchantable volume, and the model does this with an interpolation or smoothing algorithm. The first thing the model does in terms of biomass is take the merchantable volume curves and, using a system of equations that are derived from a large number of Canadian sample plots, converts the volumes to biomass for merchantable stemwood, the other pool, and foliage, and that it estimates the non-merchantable components using the smoothing algorithm. Once the total above ground biomass is known for any softwood and hardwood components of a stand, then the root biomass is predicted using equations from the listed science publications in the Canadian Journal of Forest Research. Both publications are based on large numbers of plots and studies throughout temperate and boreal forests from around the world. As stated earlier, dead organic matter dynamics are linked to the biomass dynamics. In other words, if a tree dies by being blown over or is killed by an insect pest, all of the carbon doesn't immediately escape to the atmosphere. There is a process of decomposition, unless, for example, a tree is completely combusted in a fire. What the model is representing are the dynamics of litter fall, branch fall, tree mortality, standing dead trees or snags, etc. The way that GCBM does this is that it has a series of dead organic matter pools that are defined by their turnover rates and the type of biomass that is entering into those pools. These were designed from the ground up in such a way that the pools can be related to the Intergovernmental Panel on Climate Change, or IPCC pools. The model actually has more, but they can be combined into litter, deadwood, and soil organic carbon, which are the 3 IPCC dead organic matter pools. In the model, there is a very fast pool that receives input from the short-lived fine roots and foliage. There is a fast pool that contains the submerchable biomass, small trees, branches and tops, and coarse roots. There is a medium pool which represents coarse weedy debris from fallen merchantable stemwood. And then there is a slow pool, split into above ground slow and below ground slow, that receives no direct input from the biomass, only input from decomposing humified materials from the other three DOM pools. The model also represents dead standing trees or snags. At this level, they are still divided into softwood and hardwood, and the model represents the merchantable size snag stemwood and the snag branches. The reason this is done is because even after a forest fire, dead standing trees can remain standing for a long time. The picture on the left is from Vancouver Island. The fire was in 1974 and the picture was taken in 2001. So these dead trees had been standing for 27 years, and many still are, even with branches attached. Coarse woody debris represents the downed wood, typically accumulating snags as they fall over. However, some disturbances can also transfer biomass carbon directly to this pool. There are above ground and below ground fast pools. The above ground fast pool represents the fine woody debris, so input from tops and branches, and the below ground fast pool represents coarse roots and, unfortunately, stumps. We say unfortunately because stumps should decompose in their own pool at a different rate, likely slower than coarse roots. Root and foliage litter enter the above ground and below ground very fast pools. The boundary between these two pools is the mineral soil and forest floor, and despite the name, above ground very fast is part of the forest floor. In terms of humified organic matter, there are two pools, above ground and below ground slow. The above ground slow pool represents the H layer in the humified forest floor, and the below ground slow pool represents the humified material that has decomposed below ground, as well as a small annual transfer of dissolved organic carbon from the above ground slow pool. Note that every pool transfer rate parameter is accessible and modifiable in the Archive Index database linked to the GCBM by the user. This slide displays the pool structure of the GCBM. Every one of the biomass pools has 1 to 2 designated receiving pools on the DOM side. If it's through litter fall, it always goes to a predefined pool, and if it's the consequence of a disturbance, it could go to a different pool. As such, tree mortality results in stemwood becoming snag stemwood, branches becoming snag branches, components of the other pool transferring to the above ground fast pool, and litter fall from foliage transferring to the above ground very fast pool. Coarse root biomass carbon transfers into the above ground fast pool and the below ground fast pool, and fine roots into the above ground very fast pool and below ground very fast pool. When stemwood snags fall, they go into the medium pool, while the snag branches fall into the above ground fast pool. Transfers occur between the above ground fast and very fast pools to the above ground slow pool, which in turn decays and transfers carbon into the below ground slow pool, which also receives inputs from the below ground fast and very fast pools. So in general, as biomass dies, it goes into particular dead organic matter pools, each of which can be measured. In the model, dead organic matter dynamics are calculated through inputs and losses. The inputs of biomass to the DOM pools result from 3 processes: annual litter fall and biomass turnover, for example, branch mortality, tree mortality, foliage mortality; mortality and stand breakup, for example, where a user-defined yield curve enforces a declining volume resulting in tree mortality at stand over maturity; and disturbance-related transfers, for example, transfers of live biomass to the DOM pools resulting from mortality caused by an insect pest. The carbon losses result from 2 processes: decomposition or the decay of DOM, and disturbance-related transfers and releases, for example, a wildfire that consumes fine woody debris and forest floor material and releases that carbon to the atmosphere. Decay rates are a function of the pool type, so a base decay rate is defined for each pool, and this is done at a base decay temperature of 10 degrees centigrade mean annual temperature, and then the mean annual temperature is spatially modified so that a location in northern Canada, for example, might have a potential mean annual temperature of 1 degree, while a location in coastal British Columbia might have a mean annual temperature of 9 degrees, so the decay rates for each are modified using a Q10 relationship. Q10 values are calibrated against data and vary from 1, meaning no temperature sensitivity, to 2.65, where the decay rate of the above ground very fast pool is highly sensitive to mean annual temperature. By default, the GCBM uses mean annual temperature data from a Canada-wide climate normal map, summarized by Canadian Terrestrial Ecozone. Users can provide their own temperature maps for their study region. Temperature can also vary over time, but only decay rates respond to temperature changes over time. Tree growth rates are defined by empirical yield curves which do not capture annual variation in temperature or other environmental drivers. As dead organic matter decays, two things happen. In most pools, with the exception of the very fast pools, 83% of the decomposing carbon transfers to the atmosphere, while 17% transfers to the slow pool. And the model does not represent dissolved organic carbon losses from the ecosystem. The very fast pools differ slightly in that 81.5% transfers to the atmosphere and 18.5% transfers to the slow pool. This is based on data from a 12-year Canadian research project called CIDET. This figure displays another way to view the pool structure of the GCBM, and it includes an additional pool, black carbon. However, it's currently disabled in the model and is only used for research purposes. While there's a lot of interest in pyrogenic carbon, due to a lack of national scale data on its decay in all Canadian ecosystems, it has not been enabled with default parameters. The pools on the left represent the biomass carbon pools, and they can be highly variable over time. In the middle are the dead organic matter pools that are also variable over time, but less so than the biomass, and on the right are the slow pools that are fairly stable. This slide shows an example of how the dynamics of the various pools in a lodgepole pine stand might react following mortality resulting from an insect pest disturbance. As can be seen, the biomass slowly begins to recover as the stand regrows over time. The DOM starts off high as a result of the mortality of the stand, where most of the trees are left as snags, and they slowly decompose into the various other DOM pools over time or to the atmosphere, and the slow pool remains relatively stable. Up until this point, the processes that have been discussed occur in every stand and every GCBM project as it is simulated. Next, how disturbances are handled in the model will be discussed, and these are user-defined to target specific stands in specific years of a simulation. The GCBM currently represents over 200 different disturbance and forest management types. A few are displayed here, some of which are common across Canada, while others may have been created for specific studies or applications. If you don't see a disturbance type that occurs on your land base on the model's list of disturbance types, and it has an impact on carbon, you can modify an existing disturbance type to meet your needs, or add an entirely new disturbance type to the model. Any new or revised disturbances need to have what's called a disturbance matrix defined for it. A disturbance matrix defines, for each pool in the model, the impact that a specific disturbance or management action has on carbon transfers within a stand at the time of disturbance. And each disturbance type can have a different disturbance matrix for each ecozone in the model. If you look at the images on the left, a wildfire, a harvest, and an insect pest disturbance, each will result in different carbon transfers between pools in a stand, and the fire will also result in a transfer of carbon to the atmosphere, and the harvesting will result in a transfer of carbon to the forest product sector. Here's a simplified example of a wildfire disturbance matrix, and note that there are more pools than can be shown on the slide. The column on the left represents the pools containing carbon prior to the fire, and rows at the top represent the pools, emission types, or transfer to forest products following the fire, and the values represent the percentage of the carbon pool in the column that transfers to each top row carbon pool, emission, or forest products. For example, in this wildfire matrix, 100% of the softwood merchantable carbon is killed and transferred to the softwood stem snag pool. The carbon in the softwood foliage pool, on the other hand, transfers some carbon to the above ground very fast pool, while the rest is combusted and emitted as carbon dioxide, methane, and carbon monoxide. So, disturbances can cause direct emissions from biomass and DOM to the atmosphere. They can cause exports from the forest ecosystem to the forest product sector. They can transfer biomass carbon to the DOM pools, but they can also affect the age class structure of a stand. For example, if you have a stand replacing disturbance like a wildfire, the stand age will return to age 0 on the same or a new growth curve, user's choice. While if you have a non-stand replacing insect disturbance, the stand may or may not change age class, and the growth curve may or may not change, again, user's discretion, and each of these changes will have an impact on the subsequent carbon dynamics, including the amounts of carbon in the DOM pools and decomposition rates. In the GCBM, the user must provide disturbance information as spatial layers, raster or vector, where the areas on the map are wholly disturbed in the model, and the year and type of disturbance need to be obtainable either by file naming convention or attribute data, or a combination of both. The user can also then identify the post-disturbance dynamics or transition rule, that is, what happens to the stand after the disturbance. If the user implements a stand replacing disturbance with no transition rule, the model will just assume that the stand goes back to age 0 and regrows along the original growth curve. And if the disturbance is non-stand replacing and no transition rule is defined, the model will assume that the stand remains the same age and the remaining portion will continue to grow along the same growth curve at the original volume increments. And if a stand replacing disturbance involving a land use change, for example deforestation, is implemented, only the DOM pools will continue to process for the stand after disturbance, with the results becoming increasingly unreliable as the number of years pass, as this is a forest ecosystem model and not, for example, a cropland model. So, the user can identify the post-disturbance stand type as defined by stand classifier sets, that is, transition a stand to up to 4 different stand types, identify the age following disturbance, and they can also set a regeneration delay if necessary, if trees are not expected to regrow immediately. The reason all of this is implemented is because disturbance impacts have a significant legacy on a landscape. You can see this legacy in the DOM pool comparisons between identical stands, one that was clear-cut and one that was burned in a wildfire. In the clear-cut results, the median pool is overall lower than that of fire, and you have no snags after the clear-cut because they've all been removed from the ecosystem to the forest product sector. Whereas with the wildfire, initially there's a huge amount of carbon and snags which over time begin to fall over and contribute to the median pool. So there's a long legacy, often decades, from the time of disturbance that influences the carbon balance today. This figure provides another example of the sum of the 3 possible scenarios. So here, all 3 identical stands were subjected to a different disturbance. The insect disturbance just killed the stand, but did not release the carbon. The fire released some of the carbon through emissions, and the clear-cut harvest removed a lot of the carbon to the forest product sector, and they're each growing back. But we can see that even after 50 years, there are still significant differences in the amount of DOM carbon in each as a result of each of those past disturbances. To summarize the stand level dynamics, there are the annual dynamics where in every annual time step in every stand, there is a volume over age curve that defines the volume dynamics, which are translated into carbon using the volume to biomass conversion coefficients to determine the above ground biomass components. Then, the root biomass is calculated using the equations described earlier in the presentation, and then the DOM dynamics are simulated by linking litter fall and mortality as biomass inputs and decomposition as a loss of carbon. In some stands in some years, the user can implement disturbances that transfer biomass to the DOM pools, the forest product sector, and to the atmosphere. This concludes part 1 of the science of the GCBM.